I'm one of the TAs for this class, and we're going to go ahead and get started. So, what questions do we have?
Could you do question 41 on the reading day review?
Sure. Alrighty. So, I did see those questions in the chat. We'll go through all of that in a moment. So, this is going to talk about orthogonal stuff. All right. So, orthogonality. It is more straightforward than you might think. It is basically just perpendicular in 3D. All right. That's what it boils down to. So, if I have like a line in 3D, right, and I have another pen, a different one, right? This is perpendicular, but also as I rotate it all the way around, it's always perpendicular to it, okay? So it creates this whole like sum of things, and we can't just call one of them perpendicular, so we just call the condition orthogonal, if that makes sense, okay? Think of it as basically just perpendicular. Cool? So that's the idea behind it. We talk about it a lot when we break stuff up into different parts. Here we have an x, y, z. Okay. Just think of it like you're looking at the corner of a room. All right. So if I have a vector that comes like up and over some amount, okay, comes here, all right, all right. Does this picture kind of make sense? I know it's hard to draw like 3D stuff in 2D, but think of it as like it's in the corner of a wall and it's sticking out, okay? And what we're gonna talk about is we're gonna talk about projecting onto the XZ axis, which is all the stuff down here, okay? Just like flat, like think like on a table. And this is something that is sticking out of a table and kind of like diagonal a little bit, okay? So the reason we like to talk about orthogonality is because we can break things up into easier, more digestible parts that are more important, okay? So for this vector right here, if we're projecting, all right, we're going to get a component that is on the plane, right? So it's like if my pencil is sticking off the table and I am like looking over it, okay, I'm only going to see like how it moves like along the table. I don't see how high it sticks up, okay? So that's this part right here is the projection. I'll call this vector, we'll call it A. Okay, and I'll call the x, z plane W, a space W, okay? Projection of A onto W is just the part, like the shadow of it, if you will, okay? So the part that's left, the part that physically sticks off the table, okay, this part here, that is what we call, well, we can call it a handful of things, but I like to call it the projection of W perp of A, or the projection of A onto W perp, okay? So that's the space that is orthogonal to the plane. So obviously, if you're thinking about a table, something that is orthogonal to that table is something just sticking straight up, okay? Does that make sense? Any questions on this stuff so far? This is the idea of how and why we like talking about these things. And another really important thing to note is the vector A is just equal to the projection of A onto W plus the projection of A onto W perp, okay? Think like whatever, the actual like pencil is just how far it goes across the table plus how far it goes up, okay? This is the idea here, and that's a plus there, right? So this can be very helpful in breaking down stuff. And like something else to note is from like some big higher dimension geometry. This part, the projection of A onto W, is also the closest point on W to A. Okay, your pencil's sticking straight up, right? The closest thing to it is its shadow straight down, right? You can't get any closer than that because you can't actually get off the table if we're just talking about it like that. Okay, and I say point because this here is a vector, right? But we can just take each part and call it a point, right? So if like my vector is 4, 2, I can just say like the closest point is 4, comma 2. Okay. Again, just strictly notation, like talking about points and vectors, what they are, whatever. Okay. Any questions on this stuff so far? If you have any questions again, please just stop me. Or if someone asks in the chat, that's fine too. I'll see that. And again, there aren't, not again, but there are no stupid questions. There's nothing that you could ask that somebody else in this class doesn't also want to ask, okay? Big class, somebody in the recording might have a question, and there's somebody watching the recording might have that question that they didn't get to ask. So if you think it's a stupid question, it's probably not because somebody else is thinking it too, okay? And I promise, no judgment or anything here, okay? So, cool. So this is the idea of a projection, all right? And now we talk about how to actually find what the orthogonal projection is, okay? And again, this is orthogonal projection because we're just projecting it straight down, okay? So we're getting rid of the orthogonal part, right? And this equation we write we can think about in a few different ways. We can think about it as A minus the projection of A onto W perp equals projection of A onto W, right? If I take my pencil and I subtract how much it's off the table, it's just how far it is on that table left, okay? Likewise, the original vector minus the projection of A onto W equals the projection of A onto W perp, okay? If I subtract how far I go with my pencil, I'm left with how high it goes up, okay? Cool. Yeah, so this is all the basic concept stuff of orthogonality, all right? Kind of breezing through it and going a little fast, but hopefully it makes sense. And I'm also going to send this out as a PDF as I usually do after the review. Cool. So here, there are two really big, really nice things that we like to talk about for projection stuff, okay? One is if you're projecting onto a line. All right. So the easiest way to do this, so for like say like projecting y onto the span of u, okay? So this is a formula that you can just kind of remember, do the matrix and be done, okay? It is u transpose over u dot u, okay? Which is the same thing as u transpose over the magnitude of u squared, okay? The magnitude of the vector is just like if I have u equals a, b, c, whatever, okay? The magnitude of u is equal to square root of a squared plus b squared plus c squared plus, whatever, okay? Each part squared. Think like Pythagorean theorem type stuff, okay? Again, this is just me showing some notation here. It's nothing that should scare you. It might be a little unfamiliar, but it's not anything that's hard. So the reason I write the magnitude of u squared here, okay, is because when I square this, it just gets rid of the square root, and we're just left with each part squared, which is the same thing as dotting u dot u, okay? Same thing there. So this gets us a matrix, okay? So what we do with that matrix is then we multiply it by y equals the projection of u, or the projection of y onto u. Okay. This is one of the two big things that you need to know for projections, all right? All right. This is just a formula, pretty straightforward, because remember we're going to get, is it u transpose? Yeah, it absolutely is. Because u looks like this, u transpose looks like this. So this will be a nice and big square matrix, okay? And then u dot u is just some number we have outside, okay? So this just boils down to 1 over u dot u, some matrix, whatever, and we just factor it in, okay? Don't let that scare you. And usually just keep it in fractional form. If it's like over 7, don't try to like write out all the decimals or anything like that. That's whatever. We get the point. All right. So that's the projection onto a line. It's just like a shortcut formula, okay? For the projection on anything else, it does get a little tricky, and there is a long formula, which I don't actually like using. But it's something along the lines of like A transpose parentheses A transpose inverse times A. That's a headache. I'm going to show you a way that's a little bit easier, and it's also been shown before in, like, I know I did it in Studio. It's described in Studio. They've shown it in lecture, stuff like that. So projection onto, I'll just say space, okay? God knows how big it is, all right? Technically, you could use this formula for projecting onto a line as well, okay? Projection on a line is just an easier formula, okay? So, just a little note here. This is called the standard projection matrix. Okay. All right, so projection on a space. Say that the projection of y onto span of A and B, okay? I'll just say it's 2 vectors in this case, all right? Because 2 vectors make a plane. It could be bigger, but that's kind of a headache to think about in terms of like space stuff, right? Something else to know, is it's the same question as 43 or 41, except it's just 41 is just asking like the first part of it, all right? So the method to solve this is actually using a least squares, okay? Except we go one step further. And least squares is just a formula. It is something that I very, very highly encourage you to memorize the formula for, because you should expect it to be the last problem on your final. I don't write the finals. I have no idea if that's actually true or not. But if you look at all the practice finals, the 10th question is always at least squares. So it's just like, here's 3 points, and here's a line. Solve what the least squares line is, okay? So going back to projection on the space, what we talk about here is we set the matrix A equal to AB, right? Where A and B are our columns, all right? Okay. And we have our, like, well, I'm actually going to change this just a touch and call it A1 and A2. Sorry for all of you who have to erase stuff, but it's fine as well. So I'm just doing this to write it more of like a standard notation or whatever. So, and then our like goal vector is B, which is equal to Y, all right? Yeah, I'll go over least squares soon. And yes, I believe that is Meredith. That's the same equation. But I just like the one I use better. It's just a little nicer to have that matrix. Cool. Yeah, so here, again, like we're set up like this in basically any linear algebra problem, right? So from here, we do least squares. And this is me, you can consider this as me going over least squares right now within this, okay? Least squares is trying to get as close as possible to something, all right? So, for example, if you have a bunch of points, and you're trying to get the closest line, you use least squares, all right? We're trying to get the close, in this case, we're doing something similar. We're trying to get the closest point to that vector, right? The closest point is the projection, right? Because there's nothing closer to a point than a projection onto the space, all right? All right, so here we do least squares. Something to note, something like this is a least squares plus one more step. This is important. Do not treat it just as a least squares, all right? So, how do we do least squares? Step 1, find A. A and B. Okay? 2, Find A transpose times A and A transpose times B. 3. Solve. A transpose A augmented with A transpose B. Okay? This is your least squares. Okay? This gives you, I call it like an X vector. Okay? For a least squares problem, if they are like, hey, find the equation y equals mx plus b, okay? Call it capital B. That's a really ugly capital B. Okay? Your least squares will be solving for m and b. Okay? You're going to put in y and x to get the coefficients for m and b and then go from there. Okay? I'm sure we'll go over least squares problem at some point as well, but this is basically a least squares problem in and of itself. All right? So the one additional step for find a times x equals y. Okay? But this isn't y. It is the projection of y onto w. Okay? We're getting as close as we can to y as possible, which is the projection, all right? And in this case, this is the same as me writing like equals like our b. We're just looking for the projection of b onto w, okay? Because I just named it up here, y equals b, just for whatever. So we could look at this equation here, okay? Any questions about this? I'm about to do a numerical example as well with this question. So questions on least squares. This is, yeah, it's pretty much just find A and B, solve this, and you're done. Okay. Okay. So going back to the actual question. Let me just pull up my computer so I can look at it better. So project 654 onto. Oh, before I do this, there's one more thing I want to note. Okay. Okay. Step 5. Step 5 is if looking for the projection of y onto w orthogonal, okay? So we're going to go one step further, all right? This is if it asks you explicitly, what is the projection of y onto w perp, okay? Or something along those lines. How we do it? Pretty straightforward. Y minus the projection of y onto w equals the projection of y onto w perp, okay? Okay. Any questions on this so far? Kind of just like a mini lesson review of all of this stuff revolving projections, orthogonality, and then least squares within that. Okay. Okay. So question 41 states it's asking for a single coordinate, but we're just going to do the whole problem onto 1, 0, 1, 1, 1, 0. Okay. Far so good. So what we do here is we find A. A is 1, 1, 0, 1, 1, 0, right? Just our vectors in the columns. Our B is 6, 5, 4. Okay. Now we find A transpose. There's a handful of ways to do A transpose. the way I like to think about it is I look at the diagonal, all right, from the top left corner, and I just flip everything across it, okay, including dimension stuff. So we have 1 and 1 again, okay. We have 1 down here, we have 0, 1 over here, and we have 0 down here, okay. Because we flip this stuff over here, okay. That's how we do it, transpose. Now we find A transpose times A is equal to 1, 0, 1, 1, 1, 0. Like this. And a reminder on how to multiply matrices. Okay, I like to draw connections between my columns and rows. I call them my bridges. All right. So for this top left entry, it is 1 times 1 plus 0 times 0 plus 1 times 1. Okay, all of that just boils down to 2. Okay. And that's just how to multiply matrices. Again, this should be a review looking back, but that's okay. If you need some more help with it. So doing the next one, 1 plus 0 plus 0, that's just 1. Same thing on the bottom one down here. 1 times 1 plus 1 times 0 plus 0 times 1, it's just 1. And then down here it's 2 as well. Okay, so we have that. And now we need to find A transpose B, okay, which is equal to A transpose 1, 0, 1, 1, 1, 0. And B is 6, 5, 4. Okay. So here what we're going to get is we're going to get a 2 by 1 vector, all right? Because we're going 2 rows and 1 column, right? I build these little bridges. And if I'm going too fast, please tell me to slow down. I have a tendency to go very fast sometimes. So for this top entry, we have 1 times 6, which is 6, plus 0 times 5, which is 0, plus 1 times 4, which is 4. For the next one, we have 6 times 1 is 6, and then 5 times 1 is 5. So that gives us the vector 10, 11. Okay. This stuff doesn't really mean anything to us. Okay. This is just like the formula for trying to get a step further. All right. Now we solve. Okay. This was all stuff was steps 1 and 2 from up here. Now I go to step 3, which is we solve A transpose A augmented with A transpose B. Okay. Row reduce it, solve for everything. All right. We're going to find that we're going to get the identity over here, 1, 0, 0, 1, augmented with 3, 4. This is some row reduction stuff. It's been a while, but this is still important to know, right? Cool. Okay. Sorry, today's college acceptance day, and my brother hasn't gotten into like 3 colleges, so he's still very stressed, and he's been texting me. So sorry if I'm like checking my phone or anything, because he's trying to figure that out right now. So, cool. So we take this vector here, and this is x. This is our new like x vector equals 3, 4. Okay. This is the solution for the line that's closest to whatever our given points were. Okay. So we're not done because we're looking for a projection. Okay. So we have to go one step further. We have to take our matrix A, 1, 1, 0, 1, 1, 0, multiplied by 3, 4. Okay? AX. So 1, 1, 0, 1, 1, 0, 3, 4. This gives us 7, 4, 3. Okay. 7, 4, 3 is the closest we can get to this vector from the plane created by these 2 vectors here. Okay. So we write projection of y onto w equals 7, 4, 3. And likewise, just to go like a step further, in case you guys need to see that, well, no, not in case, to show you guys that, projection of y onto w perp is equal to the actual vector 6, 5, 4 minus the projection 7, 4, 3. Okay, and this is -1, 1, 1. Okay, so that's our orthogonal distance from the plane out. Okay, this is the vector that is the orthogonal bit. Okay, something else to note is they may ask you what is the distance between this vector and this plane. Okay, all that is it is the magnitude of the orthogonal part. Okay. Once again, how to find orthogonal, how to find magnitude? Magnitude of projection of y equals square root of -1 squared plus 1 squared plus 1 squared equals √3. Okay, so another thing to say about this vector is the vector 6, 5, 4 is √3 away from the plane spanned by these two vectors. Okay, lots of stuff going on there, lots of information. But it's okay because it's just a step-by-step process. Once you got that down, you're doing pretty okay. All right. Cool. So, yeah, that is this question. Any questions about this?
Remember the distance part again? I was a little confused by that.
Yeah. Okay. So, like going back to like the pencil and desk stuff, right? If my pencil's sticking straight up, right? The actual distance from the pencil to the desk is the shortest vector between them, right? Well, like that's the shortest vector defines the distance, right? So that's our orthogonal part. That's the projection of y onto w perp defines that vector, okay? And to find magnitude, this is outside of the scope of this class, but it's called an L2 norm, all right? And what that is it is a square root of each part squared, okay? Okay. Again, that's beyond the scope of this course, but the actual calculation is not, all right? So you just take each part and you square it and you square root it, okay? Think like magnitude or like the distance formula in 3D is what this is, okay? Cool. Any other questions about this stuff? There was a lot, so please ask questions if you have any. All right. In the chat, somebody asked, talked about orthogonality. Just did that. 3B and C on the practice final. Yes, more orthogonal stuff. So this is actually a good question to go after the last one. Right? Oh, on the same note as orthogonality, before I go into this, oh, come on. I'm going to define just a simple, like, well, not simple, but I just want to talk about dot products real quick, all right? Because it's on the same note of like orthogonality stuff, right? Jesus Christ. So, dot product. What it is numerically is it is a measure of how parallel two things are. All right? The bigger the number, the more parallel. All right? There's not really a good scale for it. Okay? But if things are not parallel or perpendicular / orthogonal, they have a dot product of 0. Okay? That's why that works. Okay? So if I'm given like, and the reason that we're able to build off this transpose stuff is because if I give you two vectors similar to the ones we just had, okay, and I tell you to find a basis for W perp, okay, so what we do is we're looking for something. We're looking for a set of vectors A, B, C such that the dot product with each vector is 0. Okay. This part is not necessary for you to write every time. This is me explaining it so that it makes sense and you can do it easily. Okay. So we're looking for something such that when we dot it each time, it's equal to 0. So let's go ahead and do that. 1, 0, 1 dotted with A, B, C equals 1A plus 0B plus 0, or nope, plus 1C, okay, equals 0. And we have 1, 1, 0 dotted with A, B, C equals 1A plus 1B plus 1C, nope, 0C equals 0, okay. This is something familiar looking, all right? Call it X, or let me write. This is a null space, okay? The set of solutions to this, right, these two things, define my vectors that are perpendicular to both, right? So whenever I solve them, it's going to tell me what things what shape that vector can take, what it can look like, right? So the way to do that, or to solve these equations particularly, is to take the null space, okay? And from here, you solve the null space of A transpose, right? Because if we look, this block here is just this turned on its side, okay? Because that's what the dot product does. It lays it on its side. So that's why we can use the transpose, because it's just kind of laying it over, all right? So the null space of A transpose is equal to the column space of A perp, okay? Likewise, the columns, damn it. Column space of A transpose equals the null space of A perp. The way I like to think about this is the way you do it is you set it once and then you flip it, right? Because this is a T and this is basically an upside down T, and this is null space and this is column space. So they're just flipped. Okay? That's the easy way to remember the formula. And you won't really need the second one, just really focus on this top one here. Okay. What exactly is a column space? In this case, the column space doesn't really. The column space would be like the set of vectors that get close to it, or honestly, I don't really know the definition because we use this only in very like high level stuff for the most part. If they ask you to find the null space of A perp, you could. But the column space is just the linear combinations of the columns of the matrix, right? So it's the span of each column, and the columns here are when we turn it sideways. So, yeah. But again, focus more on this here. Again, I cannot emphasize that enough. Please know this. Okay? So that's why this formula works, okay? And that's how we can get a basis for A perp. To get a basis for A, or we'll call it basis for W, is just the column space of A, right? It's just where our vectors can reach. It's nothing extraordinarily complicated. So back to some exam 1 stuff, basically, is what that is. Ready? So, this is 3B from the practice exam. So this states that the equation AX equals that has a least squares solution of this. So what is the closest vector to it in the span? Well, that is quite lovely because essentially, when we go back to look at our steps here, Step 3 was to find x, right? Here. All right, now I'll do a different color so it's a little bit clearer. Find x. Given us that. So now all we have to do is step 4 and we're done. Okay? Because step 4 gives us the closest thing to it. We just multiply a times, in this case, our x hat is what it's called. So that's 1, 0, 0, negative 1, 3, 0 times 2/5, negative 2. So that's the vector 2/5. Nope, what the hell is that? 2/5, 2, 6/5. That goes there. Okay. They just gave us all the information to solve for the closest like input, if you will. That's what our like least square solution is. It's our closest thing that we put in to a times x to get the projection. Okay. So that's why that is meant to be just like a quick kind of like, hey, this is actually just a matrix multiplication question. Okay. Any questions on B or anything else that I've talked about at this point? Cool. All right. So looking at C, let W be the set of all vectors in R3 in the form ABA, where A and B are real numbers. Which of the following is W perp? Okay. A few ways to do this. All right. So I would do, first of all, dot product stuff just to see, that kind of gives us like an easy thing, right? Whoa. Yeah, the 6, 5 just came from me multiplying out stuff in the last question. So the way to check span is if it's orthogonal to a span, it's orthogonal to anything on the span. So we can actually just check -1, 0, 1 dotted with A, B, A. And we're going to get -A plus 0 plus A. And that is clearly equal to 0. So that is true. Right? Give me 1 second. Okay. For here, number 2, we have to check 2 cases. We have to check the first one, 1, 0, 1, and then we'll check the second case after, if we need to. So this is A plus 0 plus A, which is equal to 2A, which is definitely not 0. So that is not the case. Okay. Yes, if A is 0, then it's 0, but it's a lot less interesting when we talk about 0 vectors being dotted with stuff because it's just the 0 vector. Okay. Okay. So the null space of ABA, that is not it. I'm just trying to figure out what they're saying here because they don't write it as a matrix, so I'm just trying to see if they mean it as like a vector. Okay. Yeah. So for this one, it is not true because the null space doesn't necessarily equate to dot product stuff in this particular case because we could have like it for a specific A, B, A, okay? Let's like set A equals 3, B equals 3 as well, okay? Or let's set B to be -3, okay? All right. So we're looking here, then we're looking for the null space of 3, -3, 3. Honestly, this is just kind of like here, you know this is true right off the bat, right? So obviously we know it can't be 5. Um, so another thing to note about I, a thing I would tell you about this is always check the spans first before you check the null spaces because the null spaces are much more convoluted to talk about, okay? If we check the spans, we know that that's true. So this one cannot be true because if it's the span of the column, then it's not the same thing as the null of the transpose. Okay, those two don't line up, the transpose and the span like that. For 3, that's talking about a different yeah, that's talking about a specific case per se of like a specific A, specific B, and a specific A. Okay, we need like numeric answers because if like A is equal to 3, B is equal to 1. Okay, so then we have the null space of 3, 1, 3. Okay, and one particular case where that isn't true, all right, is if we have like an x vector of like 1, -3, 0. Okay, that's in the null space, right? But if we check if it's if we can dot it with that, that's clearly not 0. Okay. So again, my advice is to check the spans first, and then the null spaces, just try to reason through them accordingly with that. Okay, questions on this one? That one is a hard question. That has like a lot to think about and go over there. So, okay. There are no questions. I'm just going to go on. Somebody asked for 35 from the reading day worksheet. A transpose equals W. Oh, you're right. You're right. The null of A transpose is equal to the perp. So going back to this question, this space is orthogonal to this. Okay. So they're opposite entirely. So it wouldn't make sense that one is orthogonal and the other is not. The 4 is not because of that fact that somebody just said in the chat. All right, so going on to 35. Okay, dot product stuff. So they're both orthogonal unit vectors, which means they have a magnitude of 1. Okay, so dot products are nice because we can kind of treat it kind of like multiplication in that we can factor, okay? Or we can distribute, rather. So from here, we distribute and we get 3u dotted with 7, no, dotted with 4u, and then minus 8v dotted with 4u, okay? All right. And these numbers, we can multiply through like this, okay? So we take them out, we say 12u dot u minus 32v dot u, all right? And we know that they are orthogonal and unit vectors, right? So v dot u equals 0, right? Because two orthogonal things, their dot product is 0, they're not parallel at all. And u dot u is the same thing as the magnitude squared. So that's equal to the magnitude of u squared, which is equal to 12 times 1 squared, which is just 12. Does that make sense? Cool. All right. Question 9 on the practice. And if we do run out of questions, I'll just end early. So please ask questions if you have them. Yeah, so this is a whole walkthrough example of like the stuff that we talked about first. Also, you don't need to ask me stuff that's just new per se. Like you can ask me stuff from any of the exams or any like past tense stuff as well. Because it is all fair game for the final. So okay. Okay. So part I says find a basis for W. All right. So how to find a basis for W? Well, it's defined right here as essentially a null space. Okay. So it's talking about, let's let A equals 1, 1, 1. We find the null of A. So we get 1, 1, 1, augmented with 0. So this gets us equations, x1 plus x2 plus x3. I know it's not as interesting, or it should be pretty straightforward in this specific case, but I'm still going to walk through it. Okay. So this here gets us x1 equals negative x2 minus x3, because we always solve each equation one time, okay, for the lowest subscript after we row reduce, okay? And we have x2. We don't have an equation for x2, so it's just x2 equals x2. x3, we don't have an equation for it, so we say x3 equals x3. Now we put, no, from here we move to parametric form, right? We just put parentheses around everything. We say x equals x2. Well, I'll break it up. Equals negative x2 minus x3, x2, x3, which is equal to x2 times negative 1, 1, 0, plus x3, negative 1, 0, 1. Okay? So you could say, like, the null space of this, or you could say, well, that's just like how you start the problem. You're essentially finding a basis for the null space of A. So you say basis equals negative 1, 1, 0, comma, negative 1, 0, 1. So that's part I. All right. So from here, we're looking to go from this basis now to an orthogonal projection. All right. So A is our matrix, negative 1, 1, 0, 0, 1. Okay, our goal is our B. Okay, B is 2, 1, 1. And we go through the steps of solving the least squares first, okay, with the one additional step for an orthogonal projection. All right, A transpose equals negative 1, 1, 0, negative 1, 0, 1. Another way to think about the transpose is just make each column a row, and then you're done, all right? So this column is just this row. Cool, so A transpose A equals 1, 1, 0, negative 1, 0, 1, negative 1, negative 1, 1, 0, 0, 1. Okay, draw our little bridges. And from here, we're going to get 2, 1, 1, 2. Okay. Make sure I'm doing this right, because that would be rather embarrassing. Yeah, okay, cool. So far, so good. All right, so that's that. And now we have to solve A transpose times B. is negative 1, 1, 0, negative 1, 0, 1, 2, 1, 1. Okay. So this is going to give us negative 1, negative 1. Okay, now we solve. 2, 1, 1, 2, augmented with negative 1, negative 1. Also, it's totally okay if you can't do matrix math that fast. You have about 20 minutes on each question for the final, so please take your time and make sure you're doing this stuff right. So from here, I'm going to put it in row reduced echelon form. We're going to get we're going to get negative 1/3, negative 1/3. Okay. So, again, here we have one extra step. Okay. Now we have our x vector, or if you'd rather, call it x hat. Who cares? It doesn't matter. Negative 1/3, negative 1/3. Okay. Now we multiply a times that thing. Right? Because that's our least square solution, but we have to go one more step. Okay. This gives us that's 2/3, negative 1/3, negative 1/3. All right, so this is our projection of x onto w. This is just notation stuff from the problem statement, okay? It always bugs me when they aren't consistent with notation, but I guess there's nothing you can really do except know the general form and how to do it. Okay, so that's as close as we can get to that vector, right? So now we take it one step further, and we're looking for the projection of x onto w perp, which is just the part that's on the plane versus, or the total thing minus the part that's on the plane, right? You get the part that sticks straight up, so that's x minus the projection of x onto w, which is, I believe it was 2, 1, 1, minus 2/3, negative 1/3, negative 1/3. Yeah. So this gives us 4/3, 4/3, 4/3. Odd that it worked that way, but it did. So, cool, I guess. So that's how we find the projection of w perp, which is just this. It's the exact same thing. Cool. So, any other questions about this? Part 3, Part 1, Part 2, any of these? No? All right. Moving on. Problem 43 from Studypalooza. Here we have problem 43. So, believe it or not, this is actually a rank nullity question, okay? And if we think back, rank plus nullity equals number of columns, which is just n, okay? So here, let W be the subspace of R4 given by all vectors such that this statement. Find the dimension of the orthogonal component W perp. Something to note. The dimension of W plus the dimension of W perp is always equal to n, okay? So while it's not technically a rank nullity question, you can think of it exactly the same, okay? So like if we're in 3 space, right? If I have a plane, the dimension of W is 2, and the dimension of W perp is 1, because there's only one line that sticks straight off of it everywhere, okay? If we're in 3 space and I have a single line, okay, there is a whole plane of things that spin around it that are always orthogonal to it, okay? So that's a dimension of 1 for W and a dimension of 2 for W perp, okay? So essentially what I'm saying here is dimension W plus dimension W perp equals n, okay? So we know n is 4. We have 4 variables, assume it's square, okay? For all this stuff, you should assume it's square, okay? Because we're in a space R4, all right? So if you're thinking matrices, think square, stuff like that. Even if there's 0 rows, whatever. Now we have to find the dimension of W, okay? Or the dimension of W perp, but we're looking for that, so odds are we have to use dimension of W to get there. So this is defined as the null space of 1, -1, 1, 1, right? Because look at this. If you ever have an equation equals 0, you can look at yourself and say that this is the null space, right? Set of variables equals 0, that's a null space. Cool. So, going from here, what is the null space of this here? Can somebody please tell me? I eat my food. Yeah, so this has 3 free variables, which means it has a dimension of 3 for the null space, okay? So now we have 3 plus dimension of W perp equals 4. So God, I hope at this point in your academic career you can solve this equation. So the dimension of W perp equals 1. Okay, getting here is the hard part. Once you're here, it should be pretty easy. I hope. All right. Yep, so that one is 1. All right. What's next? Stochastic matrices? Yeah, I'll get there. I will absolutely do that. Somebody asked for 4B, and then I'll go into stochastic stuff. Okay. So, yeah, we'll also go over 1-to-1 and onto. I'll do that. All right, so a 3x3 matrix with an eigenvector of this. Something to note. There are matrices that have every vector as an eigenvector, okay? All right. What are they? Well, they all have the form of some number times the identity matrix, okay? So it'll look something like this. Okay. because whatever vector you put in, okay, that vector has the form A, B, C, okay, whatever it is, you're always, always, always going to get 4A, 4B, and 4C, which is 4 times our original vector, which means it's an eigenvector, okay? Another case, well, not even another case, but if that number is 0, then we just have 0, 0, 0, 0, 0, 0, 0, 0, 0. Times our vector is always just equal to 0 times our vector, right? So this is just an easy little like, hey, I know a matrix that can have every eigenvector. You want to get really, really, really particular, you could start with a null space and work your way backwards. But that is really hard, and we don't like to do that. So let's not, okay? And by really hard, I mean you have to do work opposed to just saying like the identity matrix or the zero matrix, okay? Yeah, so that's what I suggest doing. Just there's a single set of vectors or a single set of matrices that have every vector as the every vector is an eigenvector. And again, they have to be a scalar of the identity where they have all the numbers on the diagonal are the same and a 0 everywhere else. Okay. All right. So let's talk about stochastic matrices now. All right. So on the great like high level big picture thing, here we have statistics. Here we have linear algebra. Here is stochastic matrices. Amongst many other things, okay? But it's this in between stuff, right? It's both stats and linear algebra. So, some rules of stochastic matrices. 1, always have columns that sum to 1, okay? Two, always have lambda equals 1 as an eigenvector. If they say lambda equals 1, you know it's an eigenvector. I don't know why they always have to specify that, but whatever. And one eigenspace is a line. That's some big headache, whatever thing. But that's just a fact that you're expected to know. Okay, not how to get there, not the basis of it, not the proof, just the fact that every stochastic matrix has lambda equals 1 and has, and it is a line, okay? So what that means is when we have AX, okay, there is some X such that when we multiply A times X, nothing happens, okay? So if we describe a stochastic matrix as like 4 things interacting with each other and things going back and forth, okay? So some kind of crazy web of like how things interact, okay? The steady state vector happens when everything is in just the perfect proportion such that for every like step, when everybody moves, there's the same amount of people after the fact, okay? Does that make sense as like a big picture like concept thing, right? Cool. So that's why we like steady state vectors, because as we go to infinity, it eventually just approaches that. Because all of our other another note is all of our other eigenvalues are less than 1. So they always go to 0. So the only thing left is the steady state vector. Okay. So let's go on with this. Well, technically they could be negative, but that doesn't make any sense in context, so we usually just ignore it. That's not important to know. But so for like an example, I think someone asked for a specific example. The last question on the third midterm. Yes, let me see if I can get there. Hmm. Right. Come on. All right. So this you should expect to see something like. Oh, I don't actually know if this will be on your final, but um, I would expect some kind of stochastic problem, right? They like asking this sort of stuff. Currently in 22, number of customers starting in each one. Okay. So we're told to construct a stochastic matrix. All right. How we do this? It's always a square matrix defined by the number of places for n. Okay, so it's n by n, where n is the number of places. All right. So this one, so the top, move this down just a touch. No. Start is where we stop or end. Okay. So this we'll call column 1 Amras, Amaras, and because column 1 is that, row 1 has to be the same thing. Okay, the rows and columns have to correspond. That is extremely important, and otherwise this will not work. Okay, so the second row and the second column are both bens. All right, so they're given in percents. We can convert that to decimals pretty easily, right? So, what percent of people start with Amra and stay with her? That's 70%, or 0.70, right? What percent of her customers start with her and end with Ben? That is 0.30. Another thing you could do is just, even if they tell you just the 70% part, you know the second part, because the two have to add to be 1, right? 70% plus something has to be 100%. Obviously, this has to be 30%. Otherwise, there's some percent that's unaccounted for, and then we can't do stochastic matrices because we're losing stuff with every iteration. So eventually things just won't work, and it's not a stochastic matrix anymore. So always, always, always double check to make sure your columns add up to 1. Likewise, 60% of Ben's customers stay with Ben, okay? So 60% start with Ben and end with Ben. So it is not the first entry, but it is the diagonal entry, okay? I saw a lot of people get that wrong in the midterm. That's okay. That's what we're here for. You can do better on the final for it. Okay. Likewise, 40% switch. Okay. Now we're here. That's a stochastic matrix. Fantastic. We're one step down. So based on this fact up here, that there's always a lambda of 1, okay, we can just go ahead and take a minus 1i to get and start looking for our steady state vector, okay? So this becomes 0.7 minus 1 is negative 0.3, and then we leave 0.4 alone, and we actually don't even need to do the bottom row because we know they're similar. Because it's an eigenvalue, we know that our rows are going to be similar to some extent. We can just talk about the first part, all right? So the easy little trick is just to flip them and make one of them negative, right? To get the eigenvector, 0.4 and 0.3, okay? Because 0.4 times negative 0.3 is negative 0.12, 0.3 times 0.4 is positive 0.12. When we add the two together, we get 0. So that's our goal.
Can you go over that trick again?
Yeah. So switch values and make one negative. And when I say switch, I mean this is on like the right or the second column. This goes to the first entry in the eigenvector. So that the same is true for like complex eigenvalues, okay? That trick works as well, and it makes our life a lot easier because complex math is really hard. I had the blessing of grading question 5 on the last midterm with the complex eigenvalues stuff. And I had to constantly recalculate what was equivalent and not because of the way complex algebra works. So there can be a lot of different answers. This is just a quick and easy rule so you don't have to do any extra steps or anything, okay? And this is just for 2x2s, okay? If it's anything bigger, you just find the null space. You know how to do that at this point. It's a headache, but you know how to do it. And then another note is you want all to be positive. If you get a vector that's all negative, just make them all positive, okay? Because technically your eigenspace is the span of that. So you can just multiply it by -1 and it's still in the span, okay? That's just a little note. So this is our steady state, but we have to normalize it first. And what I mean by normalize is we have to make sure that the columns add to 1. So right now they add to be 0.7, okay? So what we do is we multiply 1 over whatever they add to right now to the vector, okay? And this gives us 4 over 7, 3 over 7, okay? This is our steady state vector. What this means is of all of the population, if 4/7 of them are at Amara's place and 3/7 of them are at Ben's, then each year the number that leaves Amara's is the same number that leaves Ben's, and they completely cancel each other out, so there's no like net change, okay? That's what a stochastic matrix is like talking about, and that's like the whole idea and motivation behind doing it, okay? And vector x gives the number of customers. Okay, so I actually took this a step further than you needed to. Yeah, so this is our steady state. All they asked for was a matrix A, 0.7, 0.4, 0.3, and 0.6 times some vector that describes the next year, how that works. Whatever row and column that they were, Amara was first row, first column, so she gets the first entry in our x vector, okay? So she had 210 people, so she gets a 210, and Ben had 140, so he gets a 140. And this is our A, X, okay? Just as another like big like conceptual thing. What this describes is each year's change, okay? Whatever this vector is, it becomes something else for the next year. And then we can multiply it by A to get the next year. And then we can multiply whatever that is by A to get the year after that. And then eventually you're going to hit your steady state, okay? But they just asked to like set it up to describe the next years. So you set up the steady state, you set up your inputs, and then you're done. Okay? Any questions about stochastic matrices at this time?
What happens if they asked about like the infinite condition, like as it goes to infinity or something like that?
Yes, the infinite condition is the steady state vector. But particularly, the steady state vector is our proportion, okay? So here, when they ask about the infinite condition, you have to find total population. Okay, so that's 210 plus 140, right? Because that's like how many people we start with, and that is 350 people. Okay, so you know you're starting with 350 people, and you know as like things start to cancel out and whatever, it'll be left with a proportion of 4/7, 3/7. So as all right, for a to the n x equals b, as n approaches infinity, b approaches 350 times the vector 4/7, 3/7. I believe it's just 7 times 5, so that's 50 times. Yeah, 50 times. Oh, yeah, 200 and 150. Okay, so that would be like the infinite condition. Okay, all that goes to say number of pop times steady state equals like your infinite. Okay, does that make sense? Because
Yeah, that
again,
was
as
great.
things iterate each time, huh?
That was great. Thank you so much.
Absolutely. Cool. Okay, that was stochastic matrices. 47 on Setapalooza. What time is it? 5:20. Cool. Got it. Study Palooza. $47. Oof, y'all are making me scroll. Don't think we've had a question before, a question like 30 on Study Palooza, which is good, but uh, yep, this is what you should expect your problem 10 to look like, honestly. Um, cool. Way to do this. So, a line, right? What the hell is that? Hopefully, by this point, you know what the equation for a line is. It's y equals mx plus b in slope-intercept form, okay? Which is what we usually talk about. So here, we're given a set of data points, okay? So they're asking us to do least squares to find what m and b are in this case, okay? So let's plug these things in. We have negative 22 equals negative 7m plus b for the first one. For the second one, or for the second point, we have negative 2 equals 0 plus b. For the third one, we have 6 equals 7m plus b. Okay? So, yeah. As you could probably guess from this, and you can try to solve it, this is an inconsistent system as is. Okay? The whole point of least squares is to get as close to solving an inconsistent system. That's the whole point. Okay? So from here, we can write this in a matrix form. I'm just going to switch like the sides of this, okay? So I have negative 7, 1, 0, 1, and 7, 1 for my coefficients of m and b is equal to negative 22, negative 2, and 6. Okay? Far so good? Any questions so far? Neat. After this, I'll do one-to-one and onto, and then I'll do diagonalization, invertibility, because that kind of builds off of that. And then I'll do subspace stuff. So, cool. Here, we have to solve A transpose A augmented with A transpose B. Because that is, if you know one thing about least squares, it is that you have to solve this, okay? That is the equation. That is what you do. You plug that in and you solve it, okay? So I'm just going to go ahead and skip a little step because those are some big numbers. That is $98,003 augmented with 196 negative 18. Okay, so this gives us 1001 augmented with 2 negative 6. Yeah, negative 6. Okay, so this is our M and our B, right? So M equals 2, B equals negative 6. And we're done there. Okay. So plugging into here, 2x plus minus 6. And again, this gives us like the line that's closest. If we want like the point that's closest, we would have to do that. That's a projection question. That's not a least squares question. Neat. Okay. So somebody asked, like, what definitions do you suggest that you know word by word? I mean, for midterm 1, you should know what reduced row and row echelon form are, null space and column space, okay? Those are the big ones, including an augmented matrix in there, but that's pretty straightforward. For exam 2, you should know what rank and nullity are, like the dimension of those things. You should know, for column space, you should know like the size of column space and null space. Remember, r to the number of pivots and r to the number of rows for column space, and r to the number of free variables in r to the number of columns for null space. Okay, those are the two big things. I'll write that again just so people have it written. Free variables in r to the number of columns. And this is me like saying this in this left part in quotations, just because it's like an n-dimensional space. Okay, that's the dimension of it. All right. Yep, that's column and null space. From that, you should know onto and one-to-one. Let me think off the top of my head. And all the implications with column space, or with one-to-one onto, which we'll talk about in a minute. Dimensionality, which the dimension of these things is just, well, no, not that. Dimension is just this and this, okay? For each of those are the dimension. They should always add to your number of columns, right? Your number of pivots and your number of not pivots hopefully should encompass all of your variables. If they don't, then I don't know what is neither a pivot nor a not pivot. So, yeah, one-to-one and onto. Subspaces from that. Eigenvalues, eigenspaces. Characteristic polynomial on that same vein. Algebraic geometric multiplicity, and then complex eigenvalues. You should know how to matrix multiply, how to generate a matrix from a system of equations, including like rotations, right? The rotation matrix. Rotation for a counterclockwise is, oh, what the hell is it? cosine theta, negative sine theta, sine theta, cosine theta, and if it's clockwise, theta is negative. Okay. So with that, you may need to remember some of the unit circle. Sorry. For those of you that are engineers, that's unfortunately something that you just are going to have to kind of remember because it does not go away. But so stuff like that, how to like find a matrix for like a description of something, like a reflection or a projection. You should know that for all projections, your eigenvalues are 1 and 0, and for all reflections, your eigenvalues are 1 and -1. I'm just kind of info dumping here. I'll go into any of this stuff in more detail if you ask about it, but this is just kind of like a broad overview. So, like I said, eigenvalues, eigenvectors, how to find algebraic and geometric multiplicity, and then from that, I'll also like knowing like determinants, inverses, how to find an inverse, particularly of a 2 by 2 because that's easy, and then how to do it for a larger dimension as well. Invertibility, just a check of the determinant, right? Check that the determinant is not 0. And from that, let's see, after invertibility, diagonalization on the eigenvalue, eigenvector, algebraic, geometric multiplicity stuff. And then after that, all the stuff we've been talking about, your projections, your orthogonal stuff, your orthogonal component, your stochastic matrices, yeah, all of those things. I think that's pretty much a comprehensive list of everything that's on the final. So if you know what all of those things are, you should do pretty well. Okay. Yeah, I'll do that when I'll review geometric and algebraic multiplicity when I talk about diagonalization as well. So now going on one-to-one and onto. Okay, one-to-one. So for all B, there is at most one way to get there. Onto, for all B, there is at least one way to get there. Okay, so when these two things intersect, there is exactly one way to get there in all cases, and when both conditions are true, it is called being invertible. Okay? So, how to check for one-to-one, pivot in every column. For onto, pivot in every row. And again, if it's square and has a pivot in every column, it has the same amount of pivots in rows, right? So that's the same thing both ways. As if it's square, if it has a pivot in every column, it by definition has a pivot in every row. So a picture of what one-to-one means. Think if I'm going from like a space to another space, all right? And I move it with some kind of like lens, we'll call it like this, A. All right? So we take each of our things. Nope. And for each place we go, there is no redundancy, okay? Every time we go somewhere, there's only one way to get there. There is no case where we do something like this and we can get to the same place twice, okay? That is not one-to-one. But it doesn't mean that we cover the whole space. Maybe we can only get to this red circle, okay? Like maybe there's not a start vector that gets us out here, okay? That's okay. That doesn't tell us anything about one-to-one. It's just sometimes we can't do it, and that's okay, right? For onto. Does this picture make sense when I draw this? I'm thinking of like taking this and shooting it through like a lens is what I'm like describing it as, okay? You can also just think of me like moving from one to the other, but I'm doing it by the process of A, okay? Yes, if it's both onto and one-to-one, it is by definition invertible. And I'll talk about why that makes sense in just one moment. So, if it is onto, all we care about is that we can get to every single point on this circle. Okay? We don't care how we get there. We don't care if there's a million points that go to exactly the same one, as long as we can get everywhere else as well. Okay? So that whole thing has to be colored in. There can be like redundancy. You can put two different things in and go to the same place. But we can get everywhere. We fill the whole thing. So invertibility is when both. It is when we can get somewhere, okay? We get somewhere and we know that there's only one way to get there. And we know that we cover the whole space. So since we know there's only one way to get there, we can pin exactly from where we end back to where we were, because we know that there's only one place it could have started from. That's why both conditions have to be true for it to be invertible. Okay. Let me see if I can find this. Yeah. So here's my lists that I did from the second midterm exam, which you guys can still, or midterm review, you can still go back and look at that. It's still, you guys still have access to it. Yeah, these are the longer list of things. One-to-one, at most one solution for all B. There are no free variables since you have a pivot in every column. The dimension of the column space is just the number of columns, and the dimension of the null space is 0. Those all mean that you have a pivot everywhere. For onto, again, at least one solution, and our range, going back here. Nope, that's midterm 1. Final. Our range is this red circle. That's what I drew, okay? So it's always R, the number of columns, 2, R, number of rows, and the circle is R, the number of pivots. Okay. Cool. So going back to look at that, let's review 2 again. So for it to be onto means the columns span all of our space. Okay, that's essentially what it boils down to. Yeah. Any other questions about onto and one-to-one? All right. Moving on. One-to-one and onto. So on that same note, things are invertible if these both are true. Okay, right? Invertible if with two F's, which means if and only if, pivot in all rows and columns, which means it's square. Okay. I mean, it has to be square for that to be true. So it's invertible if its determinant is not equal to 0. Okay? And as a reminder, the determinant is equal to the product of eigenvalues. So the determinant cannot be 0. And so it can't be 0, which means that the product of eigenvalues can't be 0, which means we can't have 0 as an eigenvalue. Okay, that's why that's true. Okay, all of these things are equivalent to say having a determinant that's non-zero, having no eigenvalues equal to 0, and being invertible. All of those things mean the same. Okay, and they also mean the same thing as not having a null space for a square n by n matrix. Okay, because remember that eigenspace of 0 is just your null space. Okay, because for any, I'll talk about eigen stuff in a sec. On top of this, when we move it, actually, I can just do that because we're moving. Okay. So, for eigenspace, right? Eigenvalues. Well, before I move into that, just as a statement, this means we can solve AX equals B if we only know A and B and no what and A inverse exists. Okay. Another way that you can think about like why invertible stuff, like the determinant can't be 0, is because for a 2 by 2, right? For A, B, C, D inverse, it's equal to 1 over determinant times D negative B negative C A. If determinant is 0 here, this goes to infinity, and well, it doesn't go to infinity, it goes to something else, but then that's kind of a headache, and we can't solve that because we're not doing any kind of like theoretical math right now. We're doing linear algebra, which is still hard, but it is not as theoretical as some other math. Okay, so trying to brush through all this stuff in the last 20 minutes so that you guys are as prepared as you can be. Eigenvalues are just the solutions to the determinant A minus lambda I equals 0. If you are an engineer and you have to take differential equations, if there's one thing you should take out of this class, it is how to find eigenvalues and how to find eigenvectors. It will help you tremendously in differential equations, and especially if you're doing higher order stuff, like if you're an ECE major, mechanical engineer, aerospace engineer, this stuff will come back a lot because engineers, by definition, work with differential equations all the time. That's what engineering kind of is. It's like the practice of solving problems with differential equations. So you know how to do this. It's very important. And that's just for the engineers. For the rest of you, cool. Yeah, so there's the solutions to this, and then you take the null space of A minus lambda I for each lambda to find each eigenspace. Okay, so something to note. Now we move into talking about algebraic multiplicity, okay? So from here, again, please stop me, interrupt me, say something in the chat. My previous notes, they're on the announcements that I sent out. They were attached. They're not like files for the class, so you just have to go to the announcement, and there should be an attached PDF. If there's not, email me. I'll send it to you, whatever. Cool. So now we move into algebraic multiplicity. Okay. And what this is how many times in eigenvalue, so I'll call it, because I want to write eigenvalue. An eigenvalue is a 0, 2, the determinant of A minus lambda I equals 0. Right? So essentially, how many times is the 0 of your characteristic polynomial? Your characteristic polynomial is just this worked out, right? So if I have lambda minus 4 cubed, lambda minus 1, okay, first of all, you can tell this is invertible right off the bat. Second of all, you can tell it's a 4 by 4 because we have lambda to the power of 3 and lambda to the power of 1. Those add to be 4. You know it's a 4 by 4 matrix. Yeah. This is determinant of. Okay. This lambda equals 4. Algebraic multiplicity of 3, and lambda equals 1. Algebraic multiplicity of 1. Algebraic multiplicity revolves around numbers. Single numbers, not vectors. Geometric talks about spaces, vectors, whatever. Okay? Cool. So here, cool. Something else we can tell is like the reason I knew what the determinant was right off the bat, okay, or that it's not 0, is because if we plug in like 0 for lambda here, okay, we're just solving for the determinant of A. So then we just have -4 cubed plus, times -1, which is -64 times -1, which is +64. Okay, that's just a cool little like, hey, here's the characteristic polynomial. Tell me what the determinant of A is, because again, if we set this to be 0, we're just finding the determinant of A. Cool. So that's the basis for algebraic multiplicity, and now we talk about geometric multiplicity. All this is how many linearly independent vectors make up the respective eigenspace. The easiest way to find this is to find the dimension of the null space of A minus lambda I, which is saying how many free variables in A minus lambda I. Okay? That is the easiest way to find geometric multiplicity. Cool? Geometric multiplicity must always be at least 1, because since we solved this to be 0, when we plug in that lambda, there is a null space. So there is at least one vector such that it's true. Okay? All lambda have a dimension of at least 1. And dimension, same thing as geometric multiplicity. Okay? So, but they can be at most your algebraic multiplicity. So, algebraic multiplicity always is greater than or equal to geometric. Always greater than or equal to 1. Okay? You always have to have a geometric multiplicity of at least 1. So, if you're given a characteristic polynomial with, I don't know, 15 different like lambda minus somethings, and they are all different, every single one of them, you know it's diagonalizable. Because you know that each lambda has its one it has a dimension of 1 for its eigenspace. So its algebraic multiplicity and geometric multiplicity are equal all the way around. That's me getting a touch ahead of myself, but you guys have still learned this. You've had an exam on it, regardless. So, diagonalization. If all algebraic multiplicities equal geometric multiplicities, okay? If you know you have an algebraic multiplicity of 1, you know your geometric multiplicity, you don't need to bother with it. If it is simply asking if it is diagonalizable, okay? Not if it's asking you to find it, okay? And again, to find an eigenspace, it's just the null space of A minus lambda I for that lambda, okay? So some notes. Can have lambda equals 0. Can have lambda equals some number twice, which is the same thing as saying like an algebraic multiplicity greater than 1, okay? These can happen, okay? Something to note, if all distinct lambda automatically diagonalizable, okay? Some things to note, reflections, always diagonalizable. Projections, always diagonalizable, okay? Cool. When we usually talk about diagonalization, we talk about the CDC inverse decomposition, where C is each of our eigenvectors, v1, v2, all the way to vn, and D is equal to lambda 1, lambda 2, all the way to lambda n, with zeros everywhere else. Cool. So it is these are the conditions you can have if it's diagonalizable. The geometric multiplicity must be equal to the algebraic multiplicity in all cases for all eigenvalues. Okay. For invertible matrices, they cannot have a lambda of 0. That's the only condition. They can't have a free variable. Okay. Questions on diagonalization and invertibility at this point? Orthogonal complement to a subspace. Yeah, I went over orthogonality a lot at the beginning of the lecture, so if you want to go back and watch the recording, that's okay. But what else did I say? I would go subspaces. Okay, let's try to breeze through this. Subspaces, 3 conditions. I implore you to always check the first condition before you try to do any tricks. Okay? Condition 1, 0 gives 0. Plug in 0. Does it work? If it does, step 1 complete. 2, closed, under, addition. 3, under, multiplication. Right. So, check if 0 is true. Cool. The alternate path is once you check 1, if column space or null space, subspace. Okay? You can skip the last 2 steps if you know you can put it in a matrix and describe either a column space or a null space. Okay? For 2 and 3, a little bit trickier. There's only like a handful of examples I'll ever pull on you, but let's use the example x and y such that their product is equal to 0. Okay? So we're going to check this for all 3 conditions. Check 1. Does 0 work? Yes. Check 2. Addition. Tricky. Okay, so let's give an example. 1, 0. All right. Closed under addition means, is there something I can add to this that also satisfies this condition, but when you add them together, they no longer satisfy the condition. Okay? So in this case, what essentially that boils down to is there something I can add to such that it becomes 1 and a number? Or number, not 0. Is there something I can add to it? Sure. I can add 0, 1 to it, right? Both of those satisfy the condition, but when we add them together, the resulting vector is 1, 1, and 1, 1, when we plug in here, does not satisfy the condition. So that fails, okay? We know it's not a subspace. We could be done if it asks if it's a subspace or not, okay? However, it could ask you each individual part. So is it closed under multiplication? All right. So this, the way I like to do this is I multiply by a general vector c, okay? So let's call it xy as our vector, all right? And we're multiplying that vector by c, okay? So, and this is an xy such that it satisfies the condition, all right? This isn't just some random xy. So this gives us cx times cy, and we're asking, is that equal to 0? Okay? So it gives us c squared xy equals 0. Well, we know x times y already equals 0, so does this equal 0? Yes, it does, because that's c squared times 0, because we picked an x and y such that it satisfied the condition, okay? So in this case, it is closed under multiplication, but it is not closed under addition, so it is not a subspace.
Can you explain the addition rule again, please?
Mm-hmm. Yep, so essentially what you're trying to do is you have a vector u, such that it satisfies the condition, okay? Okay. Now what we're asking is, can we find V such that it satisfies condition, but U plus V does not? Okay. And you can do this more generally. Okay. So another way to do it for this particular case is have a vector U equals U1, U2, okay? And have a vector V equals V1, V2, okay? So V U plus V equals U1 plus V1, U2 plus V2, right? This is just me adding vectors together. So now we plug it into the condition to see if it still works, okay? So we plug it in and we get U1 plus V1, U2 plus V2 equals 0, right? Because this becomes our new X, this becomes our new Y. We see if they work, okay? Cool. So now, is there some U and V that this is no longer true, okay? So honestly, they can only ask you like 3 different variations of this question such that it's tricky like this. That's why I picked like X, Y equals 0. Like multiplication is one of the tricky ones, okay? I suggest looking through your web work, looking through the practice stuff. When they give you these things, you'll notice that they're pretty similar in nature. So just try to go through those and make sure that you can reason through them and understand them. But to keep going on this, here, is there some U and V such that U1 plus V1 is non-zero and U2 plus V2 is non-zero? Sure. We know that at least one U1 and U2 have to be 0, and at least one V1 and V2 have to be 0. So what if they're opposite, okay? Because the conditions are essentially what if they're the same and what if they're opposite, right? Like if we have 0, 1 and 0, 2, right? We add them together and that's 0, 3. That satisfies the condition. That's why you can't necessarily just like find a simple counterexample or a simple example and say it's true, okay? But if you can find a simple counter example, it is false, okay? So here, on the condition that it's like 1 plus 0 and then 0 plus some number gives us 1 times a number, which is not equal to 0, okay? Probably 2, 1. Okay, does that make sense? I know I'm kind of breezing through it. I'm just trying to get to as much as I can before I have to go.
That helps.
My
Thank you.
apologies for that. Yeah, cool. Okay, invertible. Okay, 2C II is true for midterm 3. I actually don't have a blank PDF of the exam, so I'm going through Gradescope and just kind of screenshotting little bits. Obviously, I'm not revealing anybody's anything because that would be horrible, but yeah. All right, so we're asking here, which of the following statements are true? We're asking for someone asked particularly about II. Okay, here, why is it true? Okay. Oh, okay. So, it is true. Since when we plug this in, what we're doing is we're essentially distributing A of 4, 2 plus A of 1, 3. Okay. And we know 4, 2 corresponds to the eigenvalue of negative 1/2, and 1, 3 corresponds to the eigenvalue of 1. So this becomes negative 1 over 2, 4, 2, plus 1, 1, 3, equals negative 2, negative 1, plus 1, 3, equals -1, 2. Okay, so that makes that true. All right, any other questions? I still got some time and I can hang out for a little bit longer. Does anybody have anything else? Or are you totally set for the final? Or just dead from studying for the last whole day? Yeah, I get that. Okay. Well, that's